Dear viewers, this video is presented to you by Rajiv Institute of Technology, Hassan, Department of VLSI Design and Technology. I am Mrs. Ambika K, working as Assistant Professor. In this video, you are going to learn the theory and the demonstration of the 10th experiment in Digital Logic Circuits Lab. To design and implement mod n synchronous up and down counter using 7476 IC, to realize mod n counter using 7490 IC, and to realize synchronous counter using the IC 74192. The first design is a 3-bit synchronous up counter. A 3-bit synchronous up counter is going to have 8 different states. So the state diagram here it is shown. The first count is 000, then 001, 010, 011, 100, 101, 110, 111, and it again goes to the first sequence, first state 000. Totally 8 different states we can observe. For a 3-bit synchronous down counter, the first state is 111 and the last state is 000. Now, for those states, a truth table has to be built up using 7476 IC. For the 7476 IC, since it is a JK flip-flop, we require the excitation table for JK flip-flop. The excitation table is going to give us information between the present state and the next state. If the present state is moving from 0 to a next state 0, what's supposed to be the inputs provided to J and K? So with the help of the excitation table, the transition table needs to be prepared for a 3-bit synchronous up counter, and from this truth table, K-maps we are supposed to use to derive, to simplify the equations. From that we have got the equations for J0 as 1, K0 as 1, J1 as Q0, K1 as Q0, J2 Q1 ANDed with Q0, K2 Q1 ANDed with Q0. Using these equations, the logic diagram for a 3-bit synchronous up counter is built using the IC 7476. So here Q2 become the most significant bit and Q0 will become the least significant bit. Since it is a synchronous counter, the clock pulses of all these 3 JK flip-flops, it's tied to a single clock. Then we have to explore the functional diagram of the IC 7490. 7490 is basically a decade counter. A decade counter whose counts are going to vary from 0000 to 9, that is 1001. So initially it is made up of 2 counter. It can generate, the 7490 IC can generate 2 different modulus. One is mod 2, another one is mod 5. So mod 2 and mod 5, when they are tied together, we are going to get 5 into 2, 10 different states we are going to get. So this is the logic diagram that is required for BCD counter using the IC 7492. Another IC which has to be used for rigging up the circuit is 74192. 74192, it is a binary up-down counter. So it can be used as up counter, also it can be used as down counter. So that's why 2 clock pulses are given here. One is for clock up, another one is for clock down. And the input variables, the state that needs to be loaded into the IC through P0, P1, P2, P3, and output we can get at Q0, Q1, Q2, Q3. 74192 IC, the state can begin from any number. We can make the IC 74192 to count from 3 or to count from 9. So 9 should be initially loaded into a IC. For that we are going to make use of the load input variable. That load input variable we have to keep it high, and then the appropriate state has to be loaded into P0, P1, P2, P3, and we will get the corresponding outputs. So one example is to count from 5 to 8. So the initial count is 5. 5 means its binary representation is 0101. So 0101 should be loaded to P3, P2, P1, P0 by making load input as equal to. The logic diagram for a 3-bit synchronous up counter, it was designed on this digital IC trainer kit. As it was discussed earlier, a 3-bit synchronous up counter is going to make use of 3 flip-flops, and here we are using the IC 7476, which consists of JK flip-flops. So we have taken here 2 JK flip-flop, 2 7476 ICs. Each 7476 IC consists of 2 JK flip-flops. And also the equations for the J and K inputs. For the first JK flip-flop, J0 is equal to 1, K0 is equal to 1. Accordingly, the circuit was rigged up. And for the second flip-flop, J1 is equal to Q0, K1 is equal to Q0. And for the third flip-flop, J value is Q1 ANDed with Q0 and K2 Q1 ANDed with Q0. So accordingly, the circuit diagram, it has been rigged up. Now let us verify the contents of the circuit diagram. Since it is a synchronous up counter, the initial count is equal to 0 and the last count is equal to 111. Upon the occurrence of each clock pulse, the counter should be incremented by 1. So the initial count is here 0, 0, 0, 0, 0 and 0. Let us give the clock pulse. Now the count is 0, 0, 1. For the next 0, 1, 0. Next 0, 1, 1. For the next clock pulse 1, 0, 0. For the next clock pulse 1, 0, 1. Then 1, 1, 0. Then 1, 1, 1. So at the 8th clock pulse, the count would be 1, 1, 1. In the next clock pulse, it returns back to the same state as 0, 0, 0. This is synchronous up counter. The counts are ranging from 0, 0, 0 to 1, 1 and 1.